We wrap up our consideration of mechanical waves with something called standing waves, which are a bit of a contradiction in terms, we'll see why, but still follow kind of the same formulas as we've been using. The most spectacular example of interference comes when one wave encounters a wave of equal amplitude, but opposite phase and direction. So, something like this. And what we see that happens is that while the red wave is moving to the left and the cyan wave is moving to the right, and we can see that by just following their peaks, their yellow sum is not moving either way. The peak of the yellow is here and stays there. Sometimes it becomes a trough, but the location never moves. It's always the highest or lowest point. So something very strange is happening here. This wave is not traveling. It looks like a wave, but it's not moving left or right. Don't get distracted by the fact that the medium is moving up and down. The wave pattern is not changing its location. Note the peak of the red wave moves right, the peak of the cyan wave moves left as shown before, but the pattern itself stands. Any location where the waves always cancel out, where the medium is always undisturbed, is called a node. And any place where the waves combine for maximum constructive interference, where the medium goes through its maximum motion, is called an antinode. These are going to be labeled explicitly on the next page. So here we go. And we see that the nodes are the places there's no motion. There's one here, and there's one at either end. And antinodes are the ones that move from maxes to mins, side to side. Notice, of course, that none of these correspond to peaks of the red or cyan wave by themselves, because those are traveling. But when they combine to the standing pattern, we can talk about a point that just does not move. Does something similar happen when the two waves are in phase, but still opposite in direction? Yes, it does. We see something like this. They combine, and we get, again, a standing pattern. We still have nodes and antinodes. Of course, they're in different places. Instead of being at the center, the antinodes are over here. Sorry, the nodes are over here. And over here. And the antinode is in the center and at either end. But otherwise looks very similar. But how likely is it really that a wave will just happen to encounter a wave of equal amplitude and frequency, but heading in the opposite direction? Actually, it's quite likely. Remember that whenever a wave hits a terminus, it reflects. It might also invert. So we see something like this. This is a fixed end terminus. You should think for a second about what kind of reflection we get from it. At the fixed end, we get the inversion. And so it will be a wave that comes in like this, will be met by its twin coming back like that. And so what we see here in a quasi-realistic system is we get the bounce, and the wave comes back, and we get some weird quasi-standing thing. Although notice it's not really quite right because there are no nodes and there are no obvious antinodes. And we're going to come back to it because while the reflection is certainly true, we don't have the right phase match over here. And so we don't get a nice pattern. That's going to become very important. Only certain frequencies would give us the pattern we were talking about. All right, imagine plucking a string fixed at both ends. You'd get a bow that vibrates back and forth. We call this the fundamental mode of vibration for the string. Notice that it looks like half a sine curve, so the length of the string must be 1/2 the wavelength of the wave. Corresponding to the fundamental mode is the fundamental frequency of the string. We have that lambda is 2L, and the speed, of course, is lambda f, so the frequency is v over lambda, or v over 2L. For reasons that are going to become clear in a little bit, we usually denote the fundamental frequency by f sub 1. It turns out that we actually excite many different modes, an infinite number in fact. We call these harmonics, or overtones. Notice that we need the endpoints of the string to remain fixed, with no wave amplitude, meaning they must be nodes. So we need sine-like shapes that are 0 at each end. Here's the first three harmonics. The fundamental, also called the first harmonic. And then the second harmonic, which is this. Now remember that the wave is going to vary. It's going to do something more like that, but with time it's going to get smaller, and then there'll be an instant where it does this, and it's going to be a little bit larger on the other sense, and eventually it's going to be this. So we're drawing only snapshots at the ends rather than what you actually would see. we can look here and see there's sort of a pattern going on. For this one, lambda is 2L. For this one, lambda is L. And for this one, 1.5 lambda is L, which means lambda is 2/3 L. So the fundamental frequency is V over 2L. The next frequency is V over L, which is twice V over 2L, which is twice the fundamental. And then the third one would be V over 2/3 L, which is 3 halves V over L, which is 3 times V over 2L, or 3 times the fundamental. And for waves on a string, it becomes very easy that the spectrum here, this collection of frequencies, is the fundamental and then integer multiples of the fundamental. The general rule for string fixed at both ends is that lambda n is 2L over n, where n is some integer 1, 2, 3, 4, etc. The frequency then, f sub n, is n times v over 2L, which is n times the fundamental frequency f1. We often like to say that we need waves to fit on the string. What we mean here is we need to have an integer multiple of copies of the fundamental shape. This will end up being important later. Here's some nice photographs of the first three harmonics, the fundamental, n equals 2, n equals 3. Notice that for strings fixed at both ends, it's pretty easy to count off how many, because we just say how many antinodes do we have. It's hard to get the match exactly right in simulation. In real life, factors like small damping help compensate for any mismatch, but as always, there's some blurring due to limited precision. We can get pretty close, though. For this case, the mismatch isn't too bad. Notice that the amplitude eventually becomes much larger than the motion of the oscillator. That's because we're very close to the resonant frequency, so the energy transfers in very easily. Right, we see the wave is going back and growing more as it goes over. And then again, each time it echoes, essentially, we get a little bit more amplitude until we eventually get a lot of amplitude. In fact, the simulation has trouble animating it because things are moving so fast.